All right, today we're going to learn how to use the law of sines to solve for a triangle. Up to this point, we've learned how to solve right triangles. We did that with SOHCAHTOA, so sine, cosine, tangent. We even did it with secant, cosecant, and cotangent. That worked with right triangles. So in this section, we're going to move to oblique triangles, and that's triangles that have no right angles. We'll see triangles that are acute, which means that they have smaller than 90-degree angles, and obtuse, which are bigger than 90-degree angles. Now, here's a quick question. Do you remember from geometry the AAS, ASA, SSA, SSS, and SAS? What those meant were angles and sides. So that's when you're given an angle, and a side, an angle, a side, and an angle. These are the special cases that we're going to talk about with law of sines and cosines. If we have an angle, and a side, an angle, side angle, or a side, side angle, which is a special case, you can solve this with the law of sines. So the other ones we'll look at when we do law of cosines next time. If you know an angle and the side opposite to that angle, then you can use the law of sines. Here is our law of sines. It tells us that if ABC is a triangle with sides A, B, and C, then the sine of angle A over the side length A is equal to the sine of angle B over the side length B, which is equal to the sine of angle C over the side length C. When we label this on a triangle, we use capital letters for our angles. So this would be angle A, angle B, and angle C. The side lengths are across from the angle. So across from angle B, we would find side length B. Across from angle A, we would find side length A. And across from angle C, we would find side length C. And those are in lower cases. So we will use capital letters for our angles and lowercase letters for our side lengths. There's a couple things I want you to remember with that. When we are dealing with angles, we're going to round our answers to 1 decimal place. When we deal with the side lengths, we round to 2 decimal places. And one other quick reminder, since we're working with sine on this, when you put this in the calculator, you want to remember to put it in its correct mode. We're going to be dealing with mostly degree. So remember the degree mode in the calculator. You don't want to do the whole problem correctly and then have it in the incorrect mode, which messes things up. All right, when we say solve the triangle, that means we're looking for all 6 parts, the 3 angles and the 3 side lengths. So most of the time it's going to say solve this triangle. So here we're going to start with this first one. It says in ABC triangle, here is an angle, another angle, and then a side. So this would be AAS. Find the measurements of our missing pieces. So we've got 3 more pieces that are missing there due to the triangle being solved. The first thing you're going to want to do is draw a picture. It helps with the solving if you've drawn a picture and labeled it correctly. So we have ABC here for our triangle. It says angle C is 102.3 degrees. Angle B is 28.7. And then side length B is 27.4 feet. Side length B would be straight across from the B, so this is 27.4 down here. I've labeled the parts that were given. Now I can start to solve for the rest of them. In this case, the easiest next thing to find would be the last angle. Because we know triangles are 180 degrees, we can do 180 minus 102.3 minus 28.7, and we get that angle A is 49 degrees. So we found the first part. Now we're ready to do the rest. We want to set up these proportions in order to find the side lengths. We start with the one that we know. So we've got angle B, and we've got side B. So that's one I want to set up first. So I'm going to do the sine of 28.7 over 27.4. And then I just pick one to do. Since they gave us C, I'll go with C next. And so I do sine of 102.3 over the side length C, which is the one I'm looking for. In order to solve this, it is a proportion, so all I have to do is cross multiply here. So I get 27.4 times the sine of 102.3 is equal to C times the sine of 28.7. The last part to solve, these two are being multiplied, and I'm trying to get that C by itself, so I'm going to divide by sine of 28.7. Now that looks scary, but most of the work is done with the calculator. So don't let it scare you. There's a couple ways you can put this in the calculator. You can go step by step if you'd like, or you can hit the alpha y equals and do numerator over denominator, which allows it to go in as a fraction. Now, before I would get that started though, I would want to make sure that it's in degree mode. So I go to mode, degree, and it is. And so now I can start putting in my information. Up in the numerator, I would hit 27.4 times sine of 102.3. And then in the denominator, I'm going to put the sine of 28.7. And so there it is at 55.75. Remember, I keep 2 decimals since it is the side length. And that is feet, since that's the unit of measure they gave us. I'm not done solving for the triangle there because I do want all 6 parts. So I've got 3 angles now and 2 sides. So I need to do one more side. Since I had already set up this one, I'm going to use that same side, sine of 28.7 over 27.4. Now I'm going to look for side A. That's the last one I'm missing. So I would do the sine of 49 degrees, because that's angle A, over lowercase a. We cross multiply again, so I get 27.4 sine of 49 is equal to A times the sine of 28.7. We divide by the sine of 28.7. And I'm ready to put that in the calculator. Again, just like last time, you can put it in as a fraction. If you're not going to put it in as fraction, try and go one step at a time so that you don't mess up order of operations. So in this case, that would be 27.4 times the sine of 49 degrees, and then hit enter. A lot of people forget to put that parentheses, or when they hit the divide, it stays inside the sign and messes you up. Then hit divide, sine of 28.7. And so that is 43.06 feet. There are a couple checks that you want to keep in mind. The biggest angle should have the biggest side across from it. So we see that angle C is the biggest angle, so it should have the biggest side. If that didn't come out, then you know you've done something wrong. So make sure you're looking at stuff like that. All right. For our last problem, or our next problem here, we've got a word problem. It says, because of prevailing winds, a tree grew so that it was leaning 6 degrees from the vertical. At a point 30 meters from the tree, the angle of elevation to the top of the tree is 22.5 degrees. Find the height of the tree. So this is at a point 30 meters from the tree. Now it says from the vertical, so if we think about this is the vertical here, it grew leaning 6 degrees from that top. So I would go 6 degrees this way for our tree. And then this angle of elevation is the less part. So draw that diagram so you can see what's going on. So here it says the angle of elevation is 22.5. So I know this angle right here. For this one, a vertical would be 90 degrees, but it went 6 more degrees because it was leaning 6 degrees. So this angle is going to be 96 degrees. So that's the information that was given in the problem. Now we want to solve the rest of it to find the height of the tree. The height of the tree is this part right here. That's what we would be looking for. So A, B, C is what I'll go ahead and log it as. Instead of having the X here, I am going to go ahead and put the C so that you can see that is across from that angle. So we are trying to solve for the C here. I have these two angles. To find the third angle is the easiest one. Remember, that's 180 minus these two. So my angle B would be 61.5 degrees. Now, I didn't need that to answer, I didn't need that as an answer for this problem, but I need it in order to set up my proportions. Because that's the length that I have. I have the B side length. So in order to set up my proportion, which is sine of 61.5 degrees over 30, and then I get sine. I'm looking for this one, so I'm going to use this angle right here. So I get sine of 22.5 over C. We cross multiply. And then we divide by sine of 61.5. We verify it's in degree mode, and we put that in, and we get C is equal to 13.06 meters. So that would be the height of our tree there. This would be our height of our tree. All right, it tells us here that we want to be careful when we have ambiguous cases. That happens when we have side-side angles. So if you're given two sides and an angle, then you have an ambiguous case. And that means that you can have two solutions, one solution, or no solution. So if you are given side-side angle, there is a possibility that it can create two different triangles. That's what the two solutions are. It can create two solutions. It can create one triangle, or it could create no triangle. So you've got to be careful to make sure that that works. And I will show you all three cases now. So just like on the other side, we start by drawing our triangles. So we get A, B, and C here. And it gives us side length. A is 15, so I'm going to label that. Side length B is 25, so I'm going to label that. And angle A is 85. I cannot find my other two angles the way we did on the other side because I don't know what 180 minus, I don't have the other two. So we're going to start solving the triangle here. My first thing to do would be find another angle so that we can do this. So with the information given, I can set this up to be sine of 85, because that's my A angle, over 15. That's its corresponding side length. And then I've got my B side. So I'm going to set up as sine of B over 25. Now I've got my proportion set. We cross multiply. Just like we did before. And then I'm going to divide by 15 here to get the sine of B by itself. We put this in the calculator just like we did before, so I'll show you that. 25 sine of 85, and then divide by 15. And so I've got this part right here at 1.66, and it keeps going. And so let's remember how we solve for this angle. So to get this angle, we have to do the inverse sign to get it to the other side. So we would do B is equal to the inverse sign. That's the one with the little -1 on top of 1.66. And remember, you always want to do the entire thing without rounding when you're doing it in the calculator. So it's right there, so I'll show you that. We're going to hit second sign so that I could get the little -1. And then I use my arrow key to highlight the entire thing. That way I'm not rounding until the very end. I hit enter, and it tells me error. You may have noticed that already because we know we can't take this inverse sine of 1.66. That's out of our range since sine only goes from -1 to 1. This does not fit in the range, so you may have noticed that already. That's that DNE, or error, as the calculator said. That means there's no triangle that has those two sides and that angle. It does not exist. So that's what no solution would look like. There's no triangle, there's nothing else I can do for it. All right, so let's try another one. In this next case, I draw my triangle. I put in the information I know. And so we're going to start again. So I'm going to set up the first proportion, which in this case is the sine of 20.5 over 12 is equal to the sine of B over 31. We cross multiply and divide by 12. And so now we're ready to put that in the calculator. So I'm going to show you how that looks. That way you see the correct way on the calculator. We hit second and then sine to get the little -1. I'm going to go ahead and put it in as a fraction, just the way it is on my paper. So I get 31 sine of 20.5 and then 12. And so there it is, 64.78. With angles, we keep one decimal, so that's going to be 64.8. Once we have two angles, you can set up the proportions again, but it's really not necessary because to find the next angle, you can do the 180 minus 20.5 minus the 64.8. And that's way easier. So now we have all three angles. To find the last side, I would have to set up my proportion again. So I'm going to go ahead and set that up so that we can find our C. Again, I'm going to use the same one. Sine of 20.5 over 12 is equal to the sine of 94.7, because now we have that angle, over C. I cross multiply. And I divide by sine of 20.5. I keep two decimals on that one since it is a side length. Now, we said be careful with the SSAs, which that's what this is, side-side angle, because it could have more than one triangle. We just solved for one right here. To determine if we have a second one, I'll show you the easiest way. If you think about your unit circle, or when we talked about sine before, when I found this first angle, 64.8, that's right there. We know that there's another sign right here. So the calculator gave us the one in the first quadrant as 64.8. But we know that there's also a sine value right on the other side here. To find that one, I take that 180 and I subtract the 64.8. And so this is 115.2. Now, I have to verify that that will make a triangle. So I know 115.2, and I've got to check it with the angle they already gave us. So I add 20.5. Now that gives us 135.7. This is below 180. So it tells me there is a second triangle that works, because this angle will work and still give us a triangle. So now we know that our B2 is 115.2 degrees. To find our C2, I would take the 180 subtract 115.2 and 20.5. So basically subtract this right here. And I get that my C2 is 44.3 degrees. And then my last step, I would have to do this same thing to find what the corresponding side would be for this triangle. So I get my sine of 20.5 over 12. That was given, so that has to be the same. And then I do sine of 44.3 because that's my new C value over that C2. I cross multiply and divide, and we find that C2 is 23.93. So this would be the second triangle that also meets this criteria. That's what we would be doing. We're checking what triangles can meet that criteria. Since there's two of them, I would have to give both as answers. That's probably the trickiest thing we're going to find on these law of sines. All right, for this last one, I'll show you what it looks like if there isn't a second triangle, but there is one that meets that corresponding, because we saw what no triangle is. Here's what two triangles look like, and let's look at what one triangle would look like. So step one, I draw my diagram so I can see what information I'm given. I put that in as my side A, my side B, and my angle 42 degrees. So just like last time, we're going to start with the information they gave us, which is the sine of 42 over 22.6. And then I set that up as sine of B over 12 so that we can find that B angle. We cross multiply. And then we divide by that 22.6. Sorry about that. All right, so we were dividing by 22.6, and we get that our angle B, once I put that into the calculator, is 21.4 degrees. To find angle C, all I need to do is take that 180 and subtract the 42 and the 21.4. And so that gives us the 116.6 degrees. To find my side C, I set up my law of sines again. I start with the one they gave us information on, because that one's already set up right there. And then now that I have my angle C, I can set up my sine of 116.6 over side C. I cross multiply. And I divide. We get that side C is 29.4. Now, we need to check to see if another triangle meets that criteria. So we're going to do the same thing that we did on this top part here. My angle B was 21.4. So that's this one here, 21.4. So I know the second side is going to have another one that also has the same Y value. So I take 180 and I subtract 21.4 and I get 158.6. So that's the other possible triangle. However, when I take that 158.6 and I add it to the original angle of 42, I get 200.6. So with those two angles already, I'm above what a triangle can be, because a triangle can only be 180 degrees. So then we know there is no second triangle. The only one that meets the criteria is this first one we solved for. So that's what we're doing. And again, that only happens with the side angle ones. So those are the only ones you got to do that for. But now we've used the law of sines, and you've seen how that works on all of them. And you've seen how it works on these special cases. The last thing we're going to talk about today is finding the area of these oblique triangles. With the right triangles, you just did half base times height, so it was a little bit easier. With these oblique triangles that are not like that, they're not right triangles, there is a formula to find the area. It is 1/2 times the side BC and sine A. And then you'll see there's another equal sign here. That means you can use either one of these formulas. There's 3 different ones there. So it just depends on what you're given. If you're given side length B and C and angle A, you would use this one. If you were given sides A, B, and angle C, you would do this one. And if you had side length A, C, and angle B, you would use this one. So it is side, side, and then angle. That's what you're doing when you are given this information to find the area. They can even make it a little bit tricky, like one we're going to look at here, but you can use that formula there to do it. It says a pentagon is inscribed in a circle with a radius of 8 centimeters. Find the area of the pentagon. So here is our circle. We're going to put our pentagon in here. That means there's 5 sides. So there is our pentagon inscribed inside of a circle. And so our center point right here to the outside creates these triangles. Now we know from the center to the outside of a circle is the radius, and they gave that to be 8 centimeters. Since a circle is 360 degrees, and there are 5 of these little triangles in here, 360 divided by the 5 would give me 72 degrees. That means this angle right here has to be 72 degrees. So now we're ready to set up our area formula here. For this triangle, we're given this side, and this angle. So I get 1/2 times my side of 8 times my side of 8 times the sine of the angle, which is 72 degrees. See, it's not that hard because you could put that in the calculator. So you type that into the calculator, again in degree mode, and we get 30.43 centimeters squared. Now that is the area for the one triangle. So if I was just looking for the area of the triangle, that would be my answer. If we're looking for the area of the entire pentagon, we know there are 5 of these triangles. So I multiply that times 5. And so the area of the pentagon would be 152.17 centimeters squared. So there's using our law of sines, finding the area of oblique triangles. Next time, we'll continue with law of cosines.